In the next couple of videos, we are going to write our own hash table. So we are going to write a hash table to hold a very simple object of type student. So I've got a very simple class here, the student class. A student is described by an integer ID and a name, and we're going to write a hash table to store this particular type of object. Now, if we were writing a more general hash table, we would get into using generics, but I just want to focus more on how the actual hash table part works. So we're just going to write a hash table for one particular kind of object, and it's going to be this student kind of object. So the student class, again, student, I'm just describing them by an integer ID and a name. We've got getters and setters. I have the ID set to be between greater than 1 and less than or equal to the max number of students. So in this example, I'm saying that the most students we can have in our system is 99,999. So basically, students can have up to a 5-digit ID. I am assuming that IDs will be unique. Okay, so that's kind of the max number of students we're saying we can handle in our database here. I do override the equals and the hash code method, comparing for equality based on both name and ID, and then also hashing based on name and ID as well. So it's important to note that if we were not writing our own hash table, if we were just using a hash table provided in the Java Standard Library, this would be the hash code for a student object. That's why we override that hash code method, is to provide a way to calculate a hash code. So that's what would be used. But we can look at a different way of doing it because we're going to go behind the scenes and write our own hash table. And much like we've done with the other data structures in this course, the reason for walking through this kind of an example is not because out in the real world you will be very likely to write your own hash table, because most likely you will just use the hash tables provided in the Java Standard Library or by some external library. But in order to properly use those, it's good to get behind the scenes and get under the hood and really see how a hash table works so that you can have a better understanding of those other classes that you'll eventually use. So we are going to create our hash table as an array. So I'm going to just have my student hash table class, and I'm going to make a student array hash table. Okay, so again, I'm using this as type student array. If we were writing a general hash table class, I would use generics, but I don't want us to get bogged down in the syntax of the generics. I want to instead just focus on the actual hash table stuff. So that's why I'm just using this for only student objects. So that's going to be my only instance data variable, and again, it's just an array. So hash table can be pretty simple behind the scenes. In our case, we're just going to use a simple array. It's not the behind the scenes implementation that makes it so powerful. The power of a hash table comes in how you use it, how you get things in and out of the table. Okay, so it's not that there's a super complex data structure underneath, it's just how you use that data structure, in our case, how we're going to use this array. So we'll start with a constructor. And in my constructor, I am going to ask for the size to be specified. So I need to know how big you want this hash table to be. And I will use that information to create my new student array based on that size. Okay, so this is how I'm going to create my hash table. I have a little driver program here where I've created 5 student objects, and these are the objects we're going to put into our table. You can see that all of the IDs fit that requirement of their, not more than 5 digits long, so we'll be good there. And now I'm just going to create my hash table, and we're going to take a couple different approaches. So this first class we're going to write is going to be a sparse hash table. So we're going to write a very simple hashing function, and it's going to end up with a very sparse table. So the first approach we're going to use is going to use a hashing function where just a student's ID is going to be their hash code. Okay. Now again, don't get confused with the hash code method here, which is what we would be using if we were using an existing hash table class versus the hash code we're going to be creating for ourselves. So internally inside this hash table class, we're going to figure out our own approach for getting a hash code. Okay. And so in this first approach, I'm going to just, again, use the simple ID. Okay. So because of that, I'm going to say, well, okay, I know, at most you can have 99,999 students, so that's going to be the size of my hash table. I'm going to make it big enough that every student could fit in there based on their unique ID. Okay, so that's going to be the size of my hash table. So let's write some methods here. We're going to obviously want a method to add a student. So if you send me a student, I want to be able to add them to the table. And then we're also going to want a method to be able to retrieve students from our table. So I also want to have a method that gets a student And we need to think about what the parameter of that method would be. So what might be a useful method to provide for this hash table? So again, the purpose of our hash table is to store student objects and to give people an efficient way to access those objects. So if they want to put someone on the table, they actually need, obviously need to give you the student object. But if they want to get someone off the table, perhaps it would be enough to just give you their ID, to say, okay, I have the ID of this student and I want you to give me the student object based on that ID. So there are different ways you could write this kind of a get method, but we are going to take that approach and use that one. Again, it's not the only correct approach, but that's the one I'm going to look at in this example. So we're going to pass in the student ID into the get student method. And for now, just so we can compile, I'm just going to return null because we're going to start off with the add student method. So to add a student, what we want to do is we want to place that student somewhere on our array. Now, when we've looked at array-based implementations before, we have placed students based on their order in a list, for example. So if we have a list of 10 elements and we get a new element in, we put them in position 11, right? Or zero base, we put them in position 10 or whatever it is. Or if someone tells us put them in the 5th position, we shift everybody down and put them in the 5th position. But hash tables are different. They don't store things behind the scenes in a particular order. They store things based on a hash code. So what we need to do is we need to have our own internal method that is going to find the hash code of an object and use that to determine where to store it. And that method that gets that hash code, that's going to be the key to how we get things off of and put things onto or into our hash table. Okay, so I'm going to write a private helper method, get hash code, where if you give me a student, I'm going to return to you an integer, a hash code. That integer is going to represent the location in my hash table. Okay, so this gets the numeric hash code, which is the position in the hash table. Okay, now one last time, don't get confused between this hash code here, which also gives you an integer, but this is what would be used if we were using an existing hash table class. We certainly could use that, right? I certainly could say, okay, well, just return student.get student.hashcode, right? I could just use that hash code method inside my hash table class. That would be a totally valid approach. I'm going to take a different approach because it's going to allow us to look at some specific things that I want to show you, but just be aware that is one approach. So the hash code method in the student class is really the one associated with the student. But now we're writing the hash table class, and so for this class, I'm going to write my own method to get a hash code. Okay, and it's going to be a private method because nobody outside of the hash table class needs access to it. This hash code only relates to how I'm storing objects behind the scenes. It does not need to be forward facing. It does not need to be accessed by anyone else using the class. They're just going to use the class by putting students in, taking students off the table. Okay, so what we're going to do is, again, we're going to start with a very simple hash code, and essentially we are just going to use the student's ID. However, we do need to make sure that that ID is not going to be an invalid index in our table. So just to be on the safe side, even though in this example, we saw that we did make the table big enough that all of our IDs would be a valid index, we can't be, of course, certain of that as we're writing the hash table class that someone would use it in that way. So we do want to be certain about that we won't go out of bounds and crash. So we will say our hash code equals hash code mod hashtable.length. So remember how that modulus operator works. If we had a table of length 10 and someone passed in an ID of 11, well, 11 is not a valid index in the table, but if we take 11 mod 10, that gives us a value of 1, and that is going to be a valid index in the table. So you can always take this mod your table length, the size of your table, and that's going to give you a valid index somewhere in that array. And that's all we're going to do, and then we'll just return that hash code. Okay, so this is the method that generates the hash codes for my particular hash table. And what I'm saying is that I am hashing students by their student ID. So for this example, I am hashing students by their ID, and that's it. Okay, so whatever your ID is, that's essentially the slot you go in the array. If for some reason your ID is out of bounds of the array, we just take the modulus and we put you in that spot that you get from that. Okay. So that's how I'm going to get my hash code. So back up to my add student method. So I want to add in a student into my table. So what I need to do is I need to, of course, figure out where to put that student. So I'm going to get the hash code by calling the method I just wrote, sending in the student, and then I'm just going to put the student in that position. So I'm just going to say, okay, well, the hash table at that hash code gets my student. Okay. So pretty straightforward. Again, because all of my students have unique IDs, and because my table is big enough to fit the ID, the student directly in the index of their ID, that's all I have to do is just put them in the location of their ID. So no problem. So before we run some examples with this approach, I'm going to write a little helper method here called print table, just so that we can see what's going on behind the scenes. And I'm just going to write a simple loop to print out all the elements of our table, our array. So it's going to loop through my hash table.length. And I'm just going to print out both the index and the value at that index. Okay. So after we do an addition, I'm going to print the table. So we'll add the student, and then I'll print out the table so that we can see it. Okay, so let's go over to our driver program, and let's add our student. So let's go through every student on my array that I created here. And let's just add them to our table. Okay. Now, if we run this, okay, it's going to take a while for that display to keep up with that, right? So, okay, this is a problem, right? Because we have this hugely sparse table, and we only have 5 students in it. I mean, if you scroll up, all of our students are in their right place. Well, I can't even get there, but let's see if I can run that again. All of our students are in the right place, but we have all these unused spaces. And memory isn't as precious as it used to be in computing environments. So that might not seem like a problem. And maybe for, this many, there we go, there's Alex Ascalot at 99914. Maybe for this size of an example, it wouldn't be. Like maybe it's not a problem to always have a sparse table of size 100,000. But when you start dealing with the size of data sets that are common in the real world today of 1 million data points, 100 million data points, you don't want to have all that extra space being used because it's just going to slow things down and it's going to use up memory that you need for other things. So this isn't a great approach, even though it's an easy approach, right? Every student has their own spot. So that's great. So that part's good, but we have this hugely sparse table. That part is not so good. Okay, so we know we need to fix this. Before we fix this, let's just finish writing the HashTable class. So let's write our find or get student method. So to get the student, again, you're going to give me the ID, and I'm going to give you back the object associated with that ID. So what I'm going to say is the student is going to be the element at the index associated with that hash, that ID. So if a student had that ID, what location would they be in my table? Then go to that location and get the student. So what I need to do is I kind of, again, need to do the same thing here. I need to get the hash code, but this time I don't have a student object to pass in. I just have the ID. But remember that my hash function is all based on ID. So I can figure this out. I just need to actually have a separate method to do that. So I'm going to overload this method to get the hash code. And I'm going to say, well, I can give you the location in the table. I can give you the hash code if you give me the student and I just get the ID, or you just give me the ID directly. And I can do that as well, right? So I can just say, okay, well, if you give me the ID, then the hash code is just going to be the student ID modulus the table length, right? That's what I have said my hash function is. Just takes the ID and gets the table length. Now I have a little bit of repeated code here, and I never like to do that. So what I'm going to do instead is I'm going to just return, I'm going to invoke one of these methods from the other. Okay, so I basically have 2 ways that you can ask for a location in the table. Ask for that hashing index, right? So we can either give you the student, and in that case, I will get the ID and then figure out the position from that, or you just give me the ID directly and I figure out the position from that. Okay, so that we can now use in our get student method. So I will say my location is going to be get the hash code for that ID. And then I'm just going to return my hash table at that location. Now, if there is no student at that location, it's going to be null. That location will be null, and I'll just return null, which is a valid approach in a hash table if you ask for something that isn't there. I don't need to check that, in this case, this implementation, I don't need to check that the student, if there is a student here, that it's the right student with the right ID, because I know that all of my IDs are unique and everyone's in their spot based solely on their unique ID. So I don't need to do any checking to make sure that it's the, right student in the right spot. I can just return it. Okay, so this would be a very, very, again, simple hashing function that would create a very, very sparse table, but does work to uniquely hash students into a unique position. So I have students in my table based uniquely on their ID, and I can put them in and I can get them out, and all of those are going to be order 1, right? To put a student into the table, to add them to the table, I just do a little math to get the hash code, and then I just put them into the table. That's order 1. To get them out, I again just do some math to figure out the index, and then I just return an array at that index, also order 1. And we can actually go over to our driver and we'll test out our get method. We didn't actually do that. So we'll say, okay, let me say I want you to give me the student that has the ID of 99. Well, I can say, okay, well, student S equals my student table dot get student 99. And then let's print out the student that we get. And once we finish printing the whole big table, hopefully we will see Sid Slacker get printed out. And actually, while that's running, there we go. That's the correct student from the table. And it will also work correctly if we ask for a student that is not in the table, right? It's going to give us a null. So if I ask for, student number 1, it should print out a null. Okay, so again, this is a valid approach, and it keeps things order 1, so it's a valid approach, it's an efficient approach, but it has this problem with this hugely sparse table. So you might be thinking, well, can't I just reduce the size of the table? Like, why do I need one table for every possible ID? And that is the right way to be thinking. But the problem is, if we reduce that table size, you now could have the possibility that 2 students need to go in the same space. And so that's going to be a collision. And so you need to resolve that collision somehow. So once we have possible overlap in our objects that need to go in one index, we have to deal with those collisions. So that's what we're going to look at in the next video, is modifying our hash function inside our table so that we can create a smaller table, but deal with the collisions that will create.